Good morning, ladies and Justin. Good to have you here today. We are going to do sort of the other side of what we were doing yesterday. In this instance, we are given a rectangular equation, and we're going to convert rectangular equations into polar equations. And again, just like yesterday, I find these can be a challenge. Now, I do find yesterday's to have been more challenging than I find these. And I'm going to go ahead and continue and write down, like I did yesterday, the identities that are going to be helpful to us. We know that x is going to be equal to, as Justin was telling us yesterday, r cosine theta. Y is equal to r sine theta. We have x squared. We have the formula for a circle, x squared plus y squared equals r squared. And the expanded version thereof, which is like this, quantity x plus, or actually it's quantity x minus h squared plus quantity y minus k squared equals r squared. We have our reciprocal identities that cosecant theta is equal to 1 over sine theta. And finally, we have our secant theta is equal to 1 over cosine theta. So those are identities that can be helpful to us here today. Just like yesterday, right? Now, here we have x equals 2. Well, we look over here at our list, our toolkit, and we see that r cosine theta is it. So we say, okay, r cosine theta is equal to 2. Is everybody okay with that? Okay. And so what we're trying to do is get an r equals equation. And so how do we make this an r equals equation? Yeah, so Karina suggests this. If we divide by cosine theta, this is what we get. So r is equal to 2 over cosine theta. And so, and then also what we try to do is get that out of this cosine theta out of the denominator. Well, so then that becomes r equals 2 secant theta. Okay, so, but these right here are equivalent type of correct polar equations, but when we use our calculator, we're going to have to use this top one for reasons we're going to talk about shortly. This says sketch the graph of the rectangular equation. Do not use a grapher. And so we can do that. And so here's our rectangular equation, which is x equals 2. So we write this down. I'm going to do the sketch, the dashed line. So there it is. So that's x equals 2. And then it says support your hand sketch by graphing the polar equation with your grapher. So we go to our calculator and we go here, and I do not see the polar equation form. So how do we get to polar equation form? We'll go to mode and then go down to polar equation. And then I want to make sure that we're in radians, and we are. So now we're going to go here, and I would want to put 2 secant theta, but we don't have any secant capability on this calculator, so we're going to have to put 2 over cosine theta. So we go here and put this in terms of 2 over cosine theta, and there we have it. So does that look right? Yes, it does. Now, so far, does this look a little easier than what we were doing yesterday? You think so? Justin thinks so. Okay, so we'll do that. So I want you to go ahead and do number 44. We will come back to that in a minute. Yeah, do 44. And I will tell you for this one, you should get R equals 5 over cosine theta. Is that right? Is that what you got? Yeah. So it's very, very similar to 43. You have, Elizabeth, you have questions on that? Okay. One thing I remarked in this class and also in 6th period yesterday is there's something about these that I find these things kind of interesting to do. It kind of ties back what we've been doing this year. Okay, next. I want to look at 45. And 45, what 45 does is it ratchets up the complexity like we're used to. And so you have 2x minus 3y equals 5. And so you take x being r cosine theta. So I rewrite this as 2r cosine theta minus 3y sine theta is equal to 5. 3r cosine theta, excuse me. 3r sine theta equals 5. 3r sine theta equals 5. So what do you think is going to be a strategy in solving this one for r? What would you do here? What are you going to do with this one here? Is there a common factor? Yeah, so r is your common factor. So what you have is r times 2 cosine theta minus 3 sine theta are equal to 5. And so now, to solve for r, if you divide by 2 cosine theta minus 3 sine theta, and do the same thing on the right side, and so that cancels out. So r is going to be equal to all the rest of this, 5 over 2 cosine theta minus 3 sine theta. And then it says now I'm not sure about writing this thing in the numerator, because I don't know if you can because you have this separated by a negative sign. I don't know if you can flip up something to the numerator here. Probably not. But let's talk about sketch the graph of the rectangular equation without a grapher. So I'm going to do that right here. So it says 2x minus 3y equals 5. Let's solve that for y. How do you solve this for y? Well, you got negative 3y equals negative 2x plus 5. Does that make sense? Because we've taken this and subtracted it, brought it over here, and then if we divide by negative 3, divide everything by negative 3, we get y is equal to 2/3 x minus 5/3. And so negative 5/3 is our y-intercept right here. So I'll mark that right here. There's our y-intercept. And then 1, 2, 3. And then we have our slope of this is 2/3, right? So up 2 and right 3. And so we're going to look something like this. So is that what our graph should look like? Yeah. So let's go graph this in the calculator. R equals 5 over 2 cosine theta minus 3 sine theta. So I'll put 5 over 2 cosine theta minus 3 sine theta, and see what we get. I hope we get something that looks similar. Does that look about right? Yeah, it does, right? So, so this graph here verifies what we did. Now I want to ask you a question about this original equation up here. This equation up here compared to this polar equation down here. Do those equations look similar? Do they look similar? Justin thinks they do. You see some of the numbers carry over, don't you? You see the 5 here. You see the 2, you see the 3. So there is some similarity in this case, yeah. So I want you to do number 46. A similar type of problem. We'll do 47, 42. Okay, was this the equation you got for this one here? Yeah, okay. And then your rectangular equation looks like this, and then you should see something like, if I didn't make a mistake, you should see your y-intercept right here, and you should see the thing go down 3 over 4 like this. So you should see something like this. Does that look about right? Yeah, Elizabeth says so. Okay. Now what we're going to do is look to, starting in 47, we have some other things that ratchet up the complexity, as we might well expect. And here, this is what we have. So for 47, what we're going to do to convert from this, but I also want to go ahead and try to figure out what kind of circle this is going to be. This is going to be a circle. And so your circle is moved 3 units to the right and 0 units up, and your radius is 9. So you should look something like this. If your center is 3 units to the right and your radius is 3, you should get the circle, when we convert this to polar, should look something like this. Okay, that's what it should look like. So let's go ahead and convert this to a polar equation. So the first thing to do is expand this out. Well, we did binomial expansion toward the end of the first semester, and this one here is going to be x squared, and then we're going to have 2 times these first and last terms, so it's going to be minus 6x, and we have plus 9, negative 3 times negative 3, plus y squared is equal to 9. Do you see anything that cancels out? So the 9, if we subtract 9 from both sides of the equation, these 9s will cancel out, right? And then we can add 6x to both sides here. So what we have on the left side is x squared plus y squared equals 6x. What can we do next? We can replace these with our identities. So we know on the left side we're going to have r squared, right? Because x squared plus y squared equals r squared. And the right side, we have r cosine theta replacing x, so equals 6 r cosine theta. And what can we do next? What we can do is we can divide by r. If we divide by r, what do we get? Well, we get r is equal to 6 cosine theta. And let's go graph that in the calculator, see if that's what we get. And Elizabeth, I believe this section is easier than what we were doing yesterday, because we had to complete this. So we have 6 cosine theta, and then we graph, and what do we get? Doesn't look like much of a circle, doesn't it? But if we go to zoom square, we're going to square it up pretty well. Does that center look like it's at 3, 0? Okay, so anyway, that is that one worked out, our polar equation. And I want you to look at go ahead and work out 48. Oh, and I want to ask that question I asked the last time. Does this final equation here look much like the original? No, really, not at all. I mean, not at all, just totally different. So I want you to do number 48. And we'll just take it to that point. We'll do this cost. Are you having trouble with this? Justin, you able to expand this out and everything? Are you having trouble with this one? No. I mean 48. I have plenty of point of this one. I meant 48. Yeah, that's what I meant, 48. Okay, I will have my name revealed here. And I get, Justin, can you show us what you did on this one? How did you work this one out? Okay, good. And when you expanded that, what did you get for that? You should get okay, x squared. You get x squared plus y squared plus 1. Okay, you should also get minus 2y in addition to the plus 1. Where does the minus 2y come from? Let's go ahead and flesh that out. Because you're multiplying this together, when you expand the binomial, you're going to have a middle term, right? So let's go ahead and flesh that out. So we got y minus 1, y minus 1, right? So you get y squared, and that's good. And this plus 1, that's good. But also we have minus y and minus y here. So that's where your minus 2y comes from. Does that make sense? Okay, good. And what happens to this 1 over 1? Cancel, right? And so now we have, and we can add the 2y here. Is that right, Justin? So we have on the left side x squared plus y squared equals 2y. Then what? What can we replace x squared plus y squared with? R squared, right? And then here we have 2r sine theta. And then what? If we divide by r, what do we get? We get r is equal to 2 sine theta. And just before we graph this in the calculator, what is the position of our circle going to be? and size. What's our radius of the circle going to be? 1. And our center of the circle is going to be at x equals 0 and y equals 1. So here we have our center up here at 0, 1, and our radius of 1, right? That's r squared. So we should have something that looks like this. Does that look right? So let's go to the calculator. And so it should pop up right up here. Is what it should be doing, right? So 2 sine theta. There we go. Does that look right? Yeah, it does. And so that's really those exercises, and what you have in 49 and 50 is you have complications of what they look like. I want to just make sure we get to 51 and 52. And they're basically real world uses of conversion from polar coordinates to rectangular coordinates to find what their distance away is. Right, we have So again, what we have here is we have our equations x equals r cosine theta and y equals r sine theta. And these are given in polar coordinate form. So I'm going to kind of color coordinate it. So I'm going to have, for this one, x is equal to 4 cosine 12 degrees, and y is equal to 4 sine 12 degrees. And then for this other one, we have x is equal to 2 cosine 72 degrees, and y is equal to 2 sine 72 degrees. And then we can just go to our calculator. I got to make sure that we are in degrees, right? So I go up to mode and change that. So now we have 4 cosine 12 degrees and 4 sine 12 degrees. So we have 3.913 and 0.832. Okay, so that's this one right here, right? And next we have 2 cosine. I've kind of changed my color coding. So we have 2 cosine 72 degrees, 2 cosine 72 degrees, and 2 sine 72 degrees. So we get 0.618 and 1.902. Makes this 0.618, 1.902. And so basically now we have our distance. We can use our distance formula, which is going to be x2 minus x1 squared plus y2 minus y1 squared. You remember that? We find our distance. And if we just take the difference between the x coordinates, we have 3.913 minus 0.618. So we get 3.295. So we have 3.295 squared plus, what's going to go here? We're going to have y2 minus y1. And you can take them in different orders, because I took that minus that, so we can do the same thing. 0.832 minus 1.902. 0.832 minus 1.902. So negative 1.07. So we have 3.295 squared. I'll go like this. So 3.295 squared plus negative 1.07 squared and for that we get 3.464. So distance .464 miles apart. So you're taking that polar data found from a radar or something like that, and then you're able to go ahead and use our distance formula to see how far they are apart. So I think that's a pretty good little application. And what I want you to do is to do this similarly with problem 52, and then we could just call that our class for the day. How's that? Looks good. You feel like you've worked pretty hard today and yesterday? Yeah. And Elizabeth, you have like the one you missed yesterday, you have the video from yesterday's class available to you to check on what we did. Okay? I think, did you get the video for that I sent out yesterday?
I think so.
You have, yeah, I should have sent it out. And really, that'd be it. Okay, I want to thank everybody. Yeah, that'll be class for today. Thank you for working to the end of the year. It's really great.